You and I live inside an almost perfect magic trick. When you step outside at night and look up, it feels like the universe is full of stars, planets, glowing gas, and maybe even other worlds with their own stories. It looks busy, crowded, alive. Yet by every serious calculation, almost everything out there is not stars or planets at all. It is emptiness. Not just mostly empty, but so staggeringly empty that your brain quietly refuses to take it seriously. Tonight, we're going to peel that illusion apart. And if you enjoy drifting into these strange questions with us, tap like and subscribe so you do not miss the next journey. When we hear the word nothing, we think of absence. An empty glass, an empty room, an empty inbox. We imagine a place where there simply is no stuff, no air, no dust, no light, just a blank, silent void. In everyday life, that idea feels simple and obvious. You remove the objects, you see what is left, and that remainder is what you might casually call empty space. Now stretch that idea upward to the night sky. Between the Earth and the Moon, there is a huge dark gulf. Between the planets, there are even wider chasms. Between the stars, the distances become so ridiculous that we start to measure them in years of travel for light itself. And between galaxies, the gaps are so immense that it is tempting to say there is simply nothing there at all. Just blackness forever. It feels natural to think of the universe as islands of matter, floating in a limitless sea of nothing. But that picture, while comforting in its simplicity, is deeply misleading. It suggests that the important thing about reality is the islands, the stars, the planets, the galaxies, you, the stuff that glows or collides or forms mountains and oceans and cities. Space in that story is just the stage, a passive background that does not really do anything. It is the blank canvas on which the real action is painted. Modern physics quietly and rather rudely disagrees. As our instruments improved and our equations became sharper, something unsettling started to emerge. The supposed blank stage was not blank at all. The canvas had its own texture, its own tension, its own restless energy. Space itself turned out to be one of the main characters in the story of the universe, maybe even the main character, and the things we call matter are small decorations on top. To get a feel for this, imagine you have a glass of water in front of you. You remove the ice cubes, if there were any. You scoop out every grain of sand, every speck of dust. You take away all dissolved minerals, every molecule of salt, every impurity you can name. Then you remove the water molecules themselves. Hydrogen gone, oxygen gone, every atom you can point at, gone. At first glance you might say that what remains in the glass is nothing. But physics insists that even after you have removed everything you can think of, the story is not over. There are still invisible fields stretched through that space. There is still the fabric of space-time itself, flexible and responsive. There is still the lowest possible energy those fields can have, something we call vacuum energy. And there is still a pattern to how that supposedly empty region responds when you place objects or charges or light inside it. This is why scientists avoid the word nothing and prefer the word vacuum. Vacuum in physics does not mean a perfectly featureless void. It means the state of lowest possible energy for a particular patch of space, once you have taken out all the obvious particles and radiation. It is more like the ground state of a musical instrument than a mute emptiness. You can pluck it and watch how it vibrates. You can measure its subtle influence on matter and light. You can even assign it properties like pressure and energy density. Here is the really unsettling part. When we map the cosmos, add up all the matter we can see, and compare it to the vast volume of space it occupies, we find that the islands are tiny and the ocean dominates. Stars, gas, dust, planets, even dark matter, all together form a thin frosting on top of an enormous cake of vacuum. The overwhelming majority of the universe is in this vacuum state. Whatever vacuum is, it is not a side character. It is the main thing that exists. The illusion of fullness comes from how our senses work. Our eyes pick up light, so we focus on the few scattered places where light is being produced or reflected strongly. A galaxy with hundreds of billions of stars looks bright and dramatic, so we instinctively treat it as the important thing. The dark stretch of space between galaxies looks like a boring gap, so we mentally edit it out. Our brains evolved to care about dense, noisy places, not silent, thin ones. In a cosmic sense, our intuition is massively biased. There is another layer to the illusion. When you sit in your room, everything feels solid and continuous. The table is here, the walls are there, the air fills the space between. There does not seem to be any room for emptiness. Yet every one of those objects is built out of atoms that are themselves almost entirely empty. The quiet, invisible structure of space is hiding inside the wood of your desk, inside the air in your lungs, inside the bones in your hand. Empty space is not just between things, it is within them. So when we say the universe is mostly nothing, we are making a bold claim. We are saying that if you strip away your human intuition and look with mathematical eyes, you discover that what feels like the background is actually the dominant player. The gaps are not empty pauses in a cosmic sentence, they are the sentence. The matter that fascinates us is more like punctuation. Over the next parts of this story, we're going to keep pulling on this thread. We will shrink down into atoms and see how emptiness dominates their structure. We will zoom outward to the scale of galaxies and cosmic voids, where the emptiness is so extreme it borders on the absurd. We will dive into the quantum vacuum, where so-called empty space boils with activity, and into the vast future, where that vacuum shapes the final fate of everything. For now, hold on to one simple but radical idea. When you look up at the night sky, you're not just seeing distant suns scattered in a dark backdrop. You're seeing a universe whose primary ingredient is something our language calls nothing, but which physics treats as a rich, dynamic, and deeply mysterious something. The greatest mystery in the universe is not what fills space, it is space itself. In the last part, we treated the sky as our canvas and saw how much of it is simply absence. Now we are going to do something stranger. We are going to turn that same idea inward, into your own body, because the shocking truth is that the same vast emptiness that stretches between galaxies also lives inside your bones, your skin, the device you're using right now. The universe is not just empty out there, it is empty in here. Picture a single atom in your mind. School diagrams usually show a neat little ball in the centre, with smaller balls circling around it like planets around a star. It looks compact and tidy, as if most of the atom is occupied by those balls. That picture is useful for children, but as a model of reality it is wildly misleading. The real atom is mostly nothing, with a tiny dense centre and a wispy cloud of probability surrounding it. Let us build a better mental image. Imagine a huge sports stadium under the night sky. The field, the seats, the towering walls. Now place a single grain of sand in the very centre of the field. That grain of sand is the nucleus. The electrons that make the atom electrically whole are not little marbles right next to it. They are more like a faint fuzzy cloud spread through the stadium and even beyond the outer walls. Between that grain of sand and the average position of an electron, there is mostly empty space. This is not a poetic exaggeration. The nucleus of an atom is around 100,000 times smaller in diameter than the atom itself. If you scaled up an atom until it was the size of a city, its nucleus would be a pebble somewhere downtown, and the electrons would be like tiny midges flitting around the suburbs. The rest of the city would be empty air. What we call solid matter is mostly the space where nothing material resides. So why does anything feel solid at all? Why does the table resist your hand instead of letting it pass through? The answer is not that atoms are tightly packed little billiard balls. It is that the electron clouds around atoms repel each other, and that a quantum rule called the exclusion principle prevents certain particles from occupying the same state. When your hand presses on the table, you're really pushing against electric fields and quantum rules. You never actually touch the atoms themselves. You encounter a force that rises sharply as the clouds overlap, and your brain interprets that resistance as solidity. Now, take all the atoms in your body, trillions upon trillions of them, arranged into cells, tissues, organs. Every one of those atoms has that same ratio of almost nothing to almost everything. If, as a thought experiment, some cosmic engineer could squeeze out all the space inside your atoms without crushing the nuclei themselves, the remaining lump of you would be unimaginably small. You as nuclear matter might fit into something like a sugar cube. The details depend on how severe the compression is, but the core idea is the same. The person you think of as taking up volume is mostly structured emptiness. This horrifying and beautiful fact scales beyond your body. Cities, mountains, oceans, planets. They all consist of atoms that are almost entirely void. If you could somehow remove the empty space within every atom in the Earth, compressing all that nuclear material to its own density, the planet would shrink to a ball only a few tens of meters across. It would still weigh as much as the Earth, still have the same mass, but it would be small enough to fit inside a city block. The difference between a blue world and a tiny ultra-dense sphere is mostly gap. Now let us zoom back outward again. Look at the solar system. Diagrams in textbooks usually show planets lining up neatly and almost touching the Sun. In reality, the distances are ridiculous. The Earth is about 150 million kilometers from the Sun. Neptune is nearly 30 times farther. If the Sun were the size of a common door, Earth would be a tiny grain of dust a few meters away, and Neptune another grain of dust in the far distance. Between those specks there would be almost nothing. Even that is not empty in the everyday sense. There is sparse gas, a few dust grains, magnetic fields, and a thin wind of particles from the Sun. But compared to air in a room, it is nearly perfect vacuum. Many regions of interplanetary and interstellar space have fewer atoms per cubic centimetre than the best man-made vacuum chambers on Earth. In other words, the emptiest places we can build are still crowded compared to the space that lies between planets and stars. Now think about the galaxy itself. The Milky Way is a swirling disk around 100,000 light-years across, with hundreds of billions of stars. That sounds dense and crowded until you imagine each star as a single grain of sand. If you poured 300 billion grains of sand into a sphere big enough to contain Earth's orbit, you would have a solid ball of sand. But if you spread those grains out so that the average distance between each grain was like the distance between the Sun and its nearest star, you would end up with something that might as well be pure vacuum with a few lonely specks. On average, the density of the observable universe is equivalent to a few hydrogen atoms per cubic meter. Take a cube 1 meter on a side, the size of a person or a small table. On average, that entire volume of cosmic space contains less matter than your breath contains in one soft exhale. The fact that galaxies and clusters exist at all is because gravity, over billions of years, has gathered tiny excesses of matter into knots and filaments. Yet even inside galaxies, the space between stars is vast and empty compared to the scale of the stars themselves. This is the unsettling pattern that repeats at every level. Atoms are mostly gaps around tiny cores. Your body is mostly space between atoms. Planets are mostly empty space in disguise. Solar systems are scattered dots in a huge volume. Galaxies are dust in an even greater void. When you trace the ladder of scales from the nucleus up to cosmic filaments, the thing that grows overwhelmingly is not matter, it is room. Reality is architecture made from absence. There is something strangely reassuring about this. The fact that there is so much emptiness is not a flaw. It is the reason complex structures can exist. If atoms were solid little marbles pressed together with no gaps, chemistry would vanish. There would be no subtle energy levels, no delicate bonds, no flexible molecules that can fold and change shape. Without emptiness between atoms and within atoms, there would be no DNA, no proteins, no neurons, no living bodies. Emptiness is the slack in the system that allows complexity to form and evolve. We have now walked a long way down from the illusion of a full night sky to the realization that you're made of almost nothing held together by forces. But even this picture is still classical and quiet. We have talked as if the void between nucleus and electron is simply blank space. In the next part, that illusion will fall as well. At the smallest scales we know how to probe. So-called empty space is not still. It is restless, noisy, and alive with flickering activity. The nothing between things turns out to be one of the most active and important somethings in the universe. In the last part, we treated empty space as a quiet architectural element, the scaffolding that allows atoms, planets, and galaxies to exist. That picture was already strange. Now we're going to do something even stranger. We're going to look at that same emptiness with quantum eyes. When we do, the calm black canvas of space does not stay calm. It starts to shimmer. It flickers. It behaves less like a dead void and more like a restless boiling medium that never truly sits still. To understand why, we have to let go of the idea that particles are the fundamental building blocks of reality. In modern physics, the deeper idea is that fields are fundamental. A field is something that has a value at every point in space and time. There is an electric field, a magnetic field, an electron field, a field for every kind of particle we know how to describe. Even when you remove every actual particle from a region, the fields remain, stretched through that emptiness like invisible fabric. Each field has a lowest energy it can settle into, called its ground state. When you add energy in a specific way, the field responds with a ripple, and that ripple behaves like what we call a particle. A photon is a ripple of the electromagnetic field. An electron is a ripple of the electron field. So when we talk about a vacuum in this language, we're talking about all the fields in their lowest energy configuration, with no ripples big enough to count as real particles flying around. At first, that might sound like a return to our original idea of nothing. Lowest energy, no particles, no motion. Surely that should be a perfectly still, featureless state. Quantum mechanics steps in here and says, not so fast. One of the deepest rules of the quantum world is the uncertainty principle. It says that certain pairs of properties cannot both be known or fixed with arbitrary precision. Position and momentum are one famous pair. Energy and time are another. For energy and time, the uncertainty principle means that you cannot have a region of space with an exactly fixed energy for an exactly defined span of time. The more tightly you try to pin down the duration, the more room there is for the energy to wobble. Over long times, energy must be conserved very precisely. Over extremely short times, there is a bit of quantum wiggle room. The vacuum takes full advantage of that loophole. The result is that the ground state of a field is not a flat, silent line. It is jittery. There are brief, tiny fluctuations in energy that appear and disappear so quickly that they never violate the conservation rules over long periods. You can think of the vacuum as a calm ocean surface that, under strong magnification, turns out to be full of tiny ripples that constantly rise and fall. Most of the time, those ripples cancel out and the surface appears smooth from a distance, but locally there is always motion. Physicists often describe these fluctuations in terms of virtual particles. For a very short time, a particle and its antiparticle can flicker into existence, borrow a little energy from the vacuum, and then annihilate each other, returning that borrowed energy. These pairs cannot travel far or live long, and you will never catch them with a normal detector as free particles, but they leave subtle fingerprints on the behavior of real particles and fields. The word virtual here is important. It reminds us that this is bookkeeping language for very short-lived disturbances, not tiny marbles popping in and out of existence like fireflies. If this all sounds like poetic metaphor rather than real physics, there is an important question to ask. Can we actually measure any effect of these vacuum fluctuations? The answer is yes. One of the most famous examples is called the Casimir effect. Imagine placing two very flat conductive metal plates facing each other at a tiny distance apart, inside a vacuum chamber with as many real particles removed as possible. Common sense says nothing interesting should happen. There are no molecules between the plates, no air pressure, no light pushing or pulling. Yet when this experiment is performed with extreme care, the plates attract each other with a very small but measurable force. The simplest way to think about it is through the idea of allowed vibrations of the fields. Outside the plates, the quantum fields can support a wide range of ripples and modes. Between the plates, the geometry only allows certain modes to exist. The region between the plates has a slightly different pattern of vacuum fluctuations compared to the region outside. That difference shows up as a pressure that gently pushes the plates together. You could also think of it in a more down-to-earth way. The vacuum is not perfectly balanced between the plates and outside. There is a kind of mismatch in the restless activity of the fields. The universe resolves that mismatch by nudging the plates toward each other. This is not a force produced by any obvious particles knocking on the plates from the outside. It is a force arising because the vacuum itself has structure and energy. The Casimir effect is not huge. For separations on the scale of micrometers, the force is comparable to the weight of a tiny grain of sand. But in physics, the size of an effect does not decide its importance. The key point is that this phenomenon has been measured many times, with different materials and distances, and it matches the predictions based on quantum fields and vacuum fluctuations. It is one of several pieces of evidence that the vacuum is not a boring nothing but a physically active state. If we mentally zoom down to extremely small scales, things get even wilder. There is a length scale called the Planck length, created by combining the constants that describe gravity, quantum mechanics, and the speed of light. It is unimaginably small, far beyond anything we can directly probe with experiments today. Many physicists suspect that at around this scale, the smooth picture of space-time itself breaks down. The vacuum might look like a stormy foam, with space-time twisting and bubbling in bizarre ways, constantly forming and destroying tiny structures. We do not yet have a complete theory of how gravity and quantum fields fit together at that scale. String theory, loop quantum gravity, and other attempts give different visions of what the quantum vacuum looks like in that regime. Some imagine tiny vibrating strings woven into a higher dimensional geometry. Others picture space-time emerging from a network of more fundamental connections. What they share is the idea that emptiness is not simple. The closer you look, the more complicated the vacuum becomes. These tiny fluctuations are not just a microscopic curiosity. They have shaped the large-scale structure of the universe. When the universe was very young, it was hot, dense, and almost uniform, but not perfectly. The same kind of quantum fluctuations that cause virtual particles to appear and disappear would have caused tiny variations in density, with some regions just a little denser and some a little thinner. If, as many models suggest, the universe went through a brief phase of incredibly rapid expansion called inflation, those tiny variations would have been stretched to cosmic scales. Later, as the universe cooled and expanded more gently, gravity would have used those slightly denser spots as seeds. Over billions of years, matter fell into those seeds, amplifying the small differences. The result is the cosmic web of galaxies and clusters that we observe today. When we map the small temperature variations in the cosmic microwave background radiation, we're essentially seeing a fossil record of those early vacuum fluctuations, frozen in light when the universe was only a few 100,000 years old. So the next time you hear the phrase quantum vacuum, try not to imagine a sterile nothing. Picture instead an invisible ocean that fills all of space, never perfectly still, always murmuring with fluctuations. In that ocean, ripples can grow into particles, and in the very early universe, those almost imaginary ripples were stretched and amplified into the structures that later became galaxies, stars, planets, and eventually brains that could ask what emptiness really is. We have now met the vacuum at its most microscopic, and learned that what seemed to be nothing is actually a restless sea of fields and fluctuations. In the next part, we will zoom back outward again to the grandest scales we know, and watch how these tiny early tremors grew into a vast cosmic web with enormous regions of deep, haunting emptiness between its glowing threads. In the last part, we stared into the smallest scales and saw that so-called empty space is always restless. Now we're going to swing the camera in the opposite direction to the largest structures the universe has ever built. The strange twist is that those giant patterns were seeded by the same tiny quantum jitters we just met. What looks like a smooth night sky is, at truly vast scales, a tangled web of matter and vacuum. Between its glowing threads lie some of the most hauntingly empty places in existence. Shortly after the universe began, it was hot, dense, and almost uniform. Almost, but not quite. Quantum fluctuations meant some regions were ever so slightly denser, others slightly thinner. Over time, gravity treated those tiny differences like seeds. Regions with a little extra matter pulled in more, grew denser, and their gravity grew stronger. Regions with a little less matter lost out. Matter flowed away from them, and they became emptier. Give gravity billions of years, and that gentle bias sketches a pattern on the largest possible canvas. When astronomers map where galaxies actually are in huge surveys of the sky, they do not see a random spray of dots. They see long, thin filaments of galaxies, delicate threads that can stretch for hundreds of millions of light years. At the intersections of these threads sit massive knots where clusters and superclusters of galaxies gather. It is as if an invisible hand traced a three-dimensional spiderweb across the cosmos and sprinkled galaxies along its strands. This is what scientists call the cosmic web. Imagine a colossal foam of bubbles. The walls of the bubbles are where the galaxies live, woven along the filaments and sheets. The interiors of the bubbles are something else entirely. Those interiors are the voids, immense regions of space where, compared to the average, almost nothing has ever formed. In computer simulations of the universe, these voids show up naturally when you let matter evolve under gravity and cosmic expansion. Real observations reveal them too. One of the most famous is known as the Bootes void, a spherical region roughly 330 million light-years across. If that volume had the average cosmic density of galaxies, astronomers would expect to see around 2,000 of them inside it. Instead, they find only a few dozen scattered lonely islands of stars. The rest of that immense sphere is simply dark. Not absolutely empty, but so underpopulated that it feels wrong to call it a part of a galaxy-filled universe at all. Pause and imagine what it would be like to live in a galaxy near the centre of such a void. On the scale of stars and planets, your local environment could be perfectly ordinary. You might have suns, worlds, nebulae, maybe even life. But when your astronomers build big telescopes and look far beyond your home galaxy, the sky would refuse to cooperate. In almost every direction, you would see nothing beyond your local group. No rich backdrop of distant galaxies, no glowing band of cosmic structure, just a few faint smudges and then blackness. The psychological impact of that is hard to overstate. From our vantage point inside the Milky Way, deep surveys reveal galaxies in every direction as far as we can currently see. We can piece together the idea of a vast cosmic web because the sky is full of clues. A civilization inside a deep void would not have that luxury. Their universe would feel brutally small and lonely. They might never guess that beyond their dark horizons lies a rich network of matter that simply never reached them. It is tempting to picture voids as simple bubbles with sharp edges, but reality is more subtle. The boundaries between a void and the surrounding filaments are fuzzy. Galaxies near the edges of voids feel two competing influences. Gravity pulls them toward nearby filaments and clusters, where matter is denser. At the same time, cosmic expansion stretches the space between everything, and under dense regions like voids tend to expand a bit faster than average. Some galaxies fall inward toward the bright threads. Others get carried along with the overall expansion and drift deeper into the emptiness. Over cosmic time, this tug-of-war sculpts the web. Filaments act like cosmic rivers, funneling galaxies toward the biggest clusters. Voids, meanwhile, swell and merge, like soap bubbles combining into larger ones. As the universe continues to expand, galaxies in dense regions grow more tightly bound together, while the vast gaps between those regions widen. The web becomes more pronounced, yet also more isolated, with each bright node surrounded by ever thicker walls of darkness. In a universe with an accelerating expansion, driven by whatever mysterious energy pervades the vacuum, this trend only intensifies. The filaments thin out as their outer galaxies slip beyond each other's reach. Voids grow into supervoids that separate islands of structure by unimaginable distances. Far in the future, observers bound to a single gravitationally linked group of galaxies may find themselves in a situation that looks, on very large scales, a lot like living inside a giant void. The larger web will have been stretched beyond their horizon. There is a poetic symmetry in all this. At the quantum scale, vacuum fluctuations produce tiny irregularities in the early universe. Those irregularities were magnified by expansion and gravity into the foam-like structure of the cosmic web. The deepest meaning of a cosmic void is that it is a place where the vacuum won the local competition, where there was simply not quite enough matter for gravity to build much. Voids are the macroscopic face of emptiness, enlarged by billions of years of cosmic evolution. So when you picture the universe as a whole, do not imagine a solid block of stars and galaxies. Picture instead a ghostly lattice of light, delicate filaments and nodes suspended in a vast sea of almost pure vacuum. The glowing parts are real and beautiful, but they are not the default. They are the exception carved out of a background that is overwhelmingly empty. In the next part, we'll bring that emptiness back down to our own scale and ask a more immediate question. What does this vacuum do to a human body that dares to step unprotected into it? Up to now, emptiness has been something we talk about at a safe distance. Vast gaps between galaxies, invisible fields flickering in deep space, atoms full of room. In this part, the vacuum stops being an abstract idea and becomes something brutally personal. We are going to take your soft, warm, wet body and drop it into the most hostile environment there is. No suit, no helmet, no air, just you and the universe. The first thing to understand is that space itself is not cold in the way a block of ice is cold. Temperature is a measure of how fast particles are moving. In a vacuum, there are almost no particles at all, so there is nothing to touch you and steal your heat by contact. What space does have is radiation. Near a star, sunlight can roast one side of you while the other side faces a dark sky that acts like a heat sink. Your body loses and gains heat only by glowing in infrared and absorbing light, which is slower than being dunked in cold water. You do not instantly freeze solid. That part is movie myth. The real killer arrives faster and more quietly. When you step into vacuum, the air around you is gone. The pressure drops almost to zero in an instant. The air inside your lungs and the dissolved gases inside your blood are suddenly in a very strange situation. Gas always wants to expand into emptier space. If you hold your breath in that moment, the pressurized air in your chest will try to explode outward. The delicate tissue of your lungs is not designed for that. It can tear, bleed, and leak air into places it was never meant to go. This is why astronauts are trained never to hold their breath in a rapid decompression. The safest thing, if there is such a thing, is to exhale as you're exposed. Let the air rush out rather than explode outward from inside. Even if you do this perfectly, you still lose oxygen in a way your body cannot tolerate. The blood flowing through your lungs stops picking up fresh oxygen. The blood already in your arteries carries only what it has at that moment. Your brain is a greedy organ. It needs a constant stream of oxygenated blood to stay conscious. Within a few seconds, the oxygen in that stream begins to drop. You might have a brief period where you can still see and think, but it fades quickly. Most estimates based on accidents and animal experiments suggest that you would lose consciousness in roughly 10 to 15 seconds. You would not have a long period of heroic struggling. Your vision would narrow and darken. Your thoughts would fragment. Then you would simply black out, not from pain but from lack of fuel. While all this is happening, the low pressure outside is doing other strange things to your body. Liquids boil more easily when the surrounding pressure drops. In vacuum, the boiling point of water falls below body temperature. The water in your saliva and on your tongue would start to fizz and boil away. The moisture on the surface of your eyes would evaporate. The fluids in your tissues would begin to form tiny bubbles, a process called ebulism. You would swell, but not like an exploding balloon. The strength of your skin and connective tissue keeps you from bursting. You might double in volume, becoming puffy and distorted, but your body does not pop. Blood inside your vessels does not boil in the same dramatic way because your circulatory system still provides some pressure. You would not see red fountains erupt from your skin. Instead, your veins and capillaries strain against the difference between inner and outer pressure. Tiny vessels may rupture. Skin might show bruising and mottling. It is a brutal process, but it is mostly hidden under the surface. Temperature continues to work on a slower timescale. If you're in direct sunlight without a suit, the side facing the sun will heat up quite strongly. Your skin could burn. The side facing away would radiate heat into the cold of space. Over time, after you're already unconscious, your body would cool and lose moisture. In the shadow of a planet or far from any star, cooling would be slower at first, but eventually you would freeze and dry out, turning into something like a human-shaped piece of jerky. Could you survive any of this? Surprisingly, yes, but only if the exposure is very short. If you are rescued and repressurized within perhaps half a minute, there is a chance you could be revived with limited damage. There have been accidents during altitude chamber tests and pressure suit failures where people were briefly exposed to near vacuum and lived to describe the experience. They reported a feeling of saliva boiling on their tongue and then rapid loss of consciousness. Beyond that kind of window, the lack of oxygen starts killing brain cells and other organs in ways that cannot be reversed. Suppose rescue does not come. After you pass out, your heart may continue beating for a short time, but without oxygen, the rhythm becomes chaotic. Brain damage grows. Within a few minutes, the body is effectively dead even if some cells hang on. The universe does not rush the rest of the process. Without bacteria and oxygen, ordinary decay is slow. In orbit, your body might remain recognizable for a very long time, gradually tanned by ultraviolet light, bombarded by tiny particles, and slowly losing volatile chemicals to the vacuum. On longer timescales, what happens to a corpse in space depends on where it is. Near a planet, atmospheric drag and orbital decay might eventually pull it down to burn up. Near a star, intense radiation and particle winds might darken and erode it. In deep interstellar space, far from any strong source of heat or gravity, your frozen remains could drift for millions of years, gently weathered by occasional dust impacts and cosmic rays that slice through molecules like microscopic bullets. Cosmic rays are high-energy particles that zip across the universe almost unhindered by magnetic fields or matter. On Earth, our atmosphere and magnetic field shield us from the worst of them. In space, they pass through flesh and bone, breaking chemical bonds and disrupting DNA. For a living astronaut, this is a long-term cancer risk. For a dead body, it is a slow, invisible form of erosion. Over vast stretches of time, radiation would gradually break complex molecules into simpler fragments. All of this paints a grim picture, but it also reveals something deep about the vacuum. Space is dangerous not because it attacks you with claws or teeth, but because it refuses to cooperate with the fragile arrangements of pressure, temperature, and chemistry that life requires. Your body is a carefully balanced pattern maintained by air, water, gravity, and a warm blanket of atmosphere. Remove those supports and the pattern fails. The universe does not hate you. It simply does not adjust itself for your comfort. Yet humans have found a way to live and work in this environment, wrapped in thin shells of metal and fabric that hold tiny pockets of fake Earth around them. Every spacesuit and spacecraft is a portable rebellion against the vacuum, a declaration that we can step into the nothing and still carry our own small islands of air and warmth. In the next part, we will widen the lens again and look at the strange invisible ingredients that fill the vacuum between galaxies, from ghostly particles to dark matter and dark energy, and see how even the emptier spaces are crowded with things we can barely detect. In the last part, we watched the vacuum strip a human body of its illusions and its air. Now we're going to pull the camera far back again and ask a different question. If you take a huge volume of so-called empty space between galaxies and you count everything in it, what is actually there? For a long time, the answer seemed simple. A little bit of thin gas, some dust, a drizzle of starlight, and not much else. Then the universe surprised us. The most important ingredients in that emptiness turned out to be things we cannot see at all. For much of the 20th century, astronomers expected that the expansion of the universe would gradually slow down. The Big Bang set everything flying apart, gravity pulls everything together. Over immense times, those two influences should fight a long tug of war, with expansion gently decelerating as matter drags on it. The big question was whether the universe had enough matter to eventually halt and reverse the expansion, or too little matter, and therefore an eternal but slowing drift outward. In the 1990s, teams of astronomers hunted for an answer by using distant exploding stars called Type 1a supernovae as standard candles. These events have fairly consistent brightness, so by comparing how bright they appear with how much their light has been stretched by expansion, you can estimate both distance and how fast the universe was expanding when the light left them. It was a clever plan. Measure enough of these explosions at different distances and you can reconstruct the expansion history of the universe. The result landed like a quiet bomb. Instead of finding that expansion was slowing, the data showed that it was speeding up. Faraway supernovae were dimmer than expected, as if they were farther away than they should be in a universe that was gently coasting. The only way to make sense of it was to accept that some kind of energy baked into space itself was pushing everything apart, overcoming the gentle pull of gravity on the larger scales. This mysterious something earned a simple name: dark energy. Dark energy is not dark in the same way a planet is dark. It does not block light. It does not clump into objects. It seems to be an intrinsic property of the vacuum. Every cubic meter of space, no matter how empty of matter, carries a tiny amount of energy that exerts a kind of negative pressure. As the universe expands and more space comes into existence, the total amount of this vacuum energy grows. The more it grows, the stronger its push on the expansion. It is a runaway feedback that, once it dominates, causes expansion to accelerate. When cosmologists add everything up, they find that ordinary matter, the kind that makes up stars, planets, gas, dust, and you, is only a small fraction of the total energy budget of the universe. A larger share belongs to some unseen form of mass that reveals itself only through gravity. An even larger share belongs to dark energy. In other words, most of the content of the cosmos is in forms we cannot see directly, and the vacuum between galaxies is where their influence becomes most obvious. The first hint that there was more mass than meets the eye came long before the supernova story. When astronomers measured how fast stars orbit in the outer regions of galaxies, they expected those stars to move more slowly than stars near the centre. The visible matter in a galaxy is concentrated toward the middle, so the gravitational pull should weaken with distance. Instead, they found that rotation speeds remain high far out in the disk. It was as if each galaxy was embedded in an extended halo of invisible mass. Clusters of galaxies tell the same story. Their galaxies move too fast to be held together by the gravity of their visible matter alone. Hot gas trapped between the galaxies emits X-rays, showing that the cluster as a whole is much more massive than its stars alone can explain. Gravitational lensing, the bending of light by mass, reveals even more. Light from background galaxies is distorted in ways that match the presence of large, unseen clumps of mass spread through and around the visible structures. The simplest explanation is that there is some kind of dark matter that interacts with gravity but not with light. Dark matter does not shine, it does not absorb, and it hardly collides with itself. It flows almost freely through ordinary matter. Right now, as you sit here, vast numbers of dark matter particles, whatever they are probably streaming through your body and the Earth with almost no effect. We do not yet know what they are made of. Many experiments have tried to catch a rare collision between a dark matter particle and an atomic nucleus in deep underground detectors. So far, the universe has kept that secret. All we really know is that without this invisible mass, galaxies and clusters would not look or behave the way they do. Between the stars, and especially between galaxies, there is also a more familiar ingredient: gas. The interstellar medium inside galaxies and the intergalactic medium between them are filled with hydrogen and helium in various forms. Some regions contain cold neutral gas, other regions are hot ionized plasma heated by supernovae and shock waves. There are thin wisps of heavier elements, traces of past generations of stars. In cosmic filaments between clusters, much of this gas is in a warm to hot state, hard to detect but real. It is so tenuous that a cubic meter might contain only a few atoms, yet across the vast volumes of interstellar and intergalactic space, it adds up. Dust grains drift through this gas. They are tiny bits of carbon, silicates, and ice. Dust absorbs and scatters starlight, reddening and dimming distant objects. It also acts as a kind of chemistry lab. Molecules form on dust grain surfaces, including complex organic molecules that are the precursors of the chemistry of life. In dense clouds, dust helps gas cool and collapse into new stars and planets. So even in regions that look black to our eyes, there is a slow, quiet cycle of matter shaping future worlds. Invisible particles called neutrinos stream through all of this. Neutrinos are produced in enormous numbers in the nuclear reactions that power stars and in violent events such as supernovae. They hardly interact with matter at all. Trillions of them pass through your body every second without leaving a trace. They fly straight through planets, stars, even whole galaxies as if they were not there. Space may look empty, but in terms of neutrinos it is a raging river. Magnetic fields thread through the vacuum too. Galaxies have large-scale magnetic fields that spiral along their disks and extend into their halos. Smaller fields wrap around stars and planets. In the thin gas between galaxies, weaker magnetic fields lurk, influencing how charged particles move and how cosmic rays propagate. We cannot see these fields directly with our eyes, but they shape the behavior of the plasma filling interstellar and intergalactic space, guiding particles along invisible lines. Layer all of these ingredients together and the picture of emptiness changes. Dark energy quietly drives the expansion of space itself. Dark matter forms scaffolding, a hidden skeleton of mass on which galaxies and clusters assemble. Thin gas and dust drift in the gaps, illuminated now and then by starlight or shock waves. Neutrinos stream through, almost unstoppable. Magnetic fields and radiation tie everything together in subtle ways. What looked like pure nothing between galaxies turns out to be a crowded, complex environment dominated by things our senses cannot directly detect. So when we say the universe is mostly empty, we're really saying that it is mostly devoid of dense luminous matter. The vacuum is not a blank canvas. It is a dynamic medium whose properties control the expansion of the universe, the formation of structure, and the fate of everything in it. In the next part, we will see how that same fabric of space and its strict speed limit conspire to isolate worlds and galaxies from one another, and how black holes turn regions of the vacuum into one-way traps from which even light can never return. Out in the dark between the stars, emptiness does something subtle but profound. It separates, not just by distance, but by the rules it obeys. We usually think of separation in simple terms. Two towns are far apart, two planets are farther, two galaxies unimaginably farther still. You could imagine that with a fast enough ship and enough patience, You could always close the gap. The universe quietly shakes its head. Built into the fabric of the vacuum is a speed limit and a way of warping that fabric that turns separation into something far more absolute. To see this in action, picture a tiny machine we already sent into that darkness. Voyager 1. It left Earth in the 1970s, flew past the giant planets, and eventually pierced the outer boundary of the Sun's influence into interstellar space. Today, it drifts in a region where the solar wind has faded and the thin gas between the stars dominates. The sky around it is black, not because nothing exists, but because the stars are so distant that they barely create a glow on its tiny cameras. The vacuum there is almost perfect. A handful of particles per cubic centimetre, a whisper of magnetic field, and that is all. Yet Voyager is never truly alone. It talks to us very slowly. Radio signals from Earth race outward at the fastest speed nature allows, the speed of light. They take many hours to reach the spacecraft. Voyager replies with its own faint beam of radio waves which take the same long journey home. Each exchange is a conversation in extreme slow motion, stretched by distance and bound by a universal limit. No amount of engineering can make those signals arrive faster. The vacuum itself refuses. This speed limit is one of the deepest features of reality. In empty space, all observers, no matter how they move, measure the same value for the speed of light in vacuum, roughly 300,000 kilometers per second. That sounds enormous until you start stacking up cosmic distances. Light from the Sun takes about 8 minutes to reach Earth. Light from the nearest star system takes more than 4 years. Light from the center of our galaxy needs tens of thousands of years to arrive. Light from some distant galaxies has been travelling toward us for billions of years, starting long before Earth even existed. Because of this, every look into space is also a look into the past. The farther out you gaze, the younger the universe you see. There is no way around this. If you sit on Earth and watch a galaxy whose light has taken 10 billion years to reach you, you will never know what that galaxy looks like right now in your present moment. You always see the version that lived 10 billion years ago. The vacuum between you and that galaxy is not just empty room. It is a huge delay baked into the structure of reality. This delay creates horizons. Imagine drawing a sphere around you, centered on your position in space, whose radius is the distance light could have traveled since the Big Bang. Everything inside that sphere has had time, in principle, to send a signal that could reach you now. Everything outside has not. That boundary is called the observable universe. It is not a wall made of matter. It is a limit set by the age of the universe and the finite speed of light. Beyond it, reality continues, but you can never see or influence it. The situation is even more dramatic when you add cosmic expansion. Space itself is stretching. Distant galaxies are carried away from us by this expansion, and the farther they are, the faster they appear to recede. Beyond a certain distance, this recession speed becomes greater than the speed of light. That does not violate the rule, because nothing is moving through space faster than light. Instead, the space between is simply increasing. But the effect is the same. Light they emit now will never reach us. They slide beyond a different kind of horizon, one of causal contact. The vacuum is pulling them out of our reach forever. Relativity goes further and tells us that the vacuum is not a rigid stage. It bends and warps in the presence of mass and energy. This curvature of space-time changes how objects move and how time flows. Clocks on a satellite orbiting Earth tick at a slightly different rate than clocks on the ground. Clocks near the surface of a neutron star run slower compared to clocks far away in empty space. Even our GPS systems have to account for these tiny differences. The vacuum around massive objects is stretched and tilted in subtle ways. As you move faster through space, your own passage through time changes relative to others. A traveller who flies on a near light speed journey and returns will have aged less than the siblings who stayed at home. This is not an illusion or a trick of perspective. It is a real difference in how their paths through space-time were traced. The vacuum offers many possible routes between events, and different routes correspond to different experience times. In this sense, empty space is not neutral. It actively shapes the story of who can meet whom and when. Black holes are where these ideas become extreme. Start with a massive star that has exhausted its nuclear fuel. Without the outward push of radiation from fusion, gravity wins. The star collapses. If the mass is high enough, no known force can stop that collapse. The matter falls inward until it forms a region so compact that the escape speed from its surface exceeds the speed of light. At that point, an event horizon forms. This is a sphere around the collapsed object that marks a one-way boundary. Cross it heading inward, and every possible future path leads deeper inside. There is no path that takes you back out into the wider universe. From the outside, a black hole is surprisingly simple. It can be described completely by just a few numbers: mass, spin, and electric charge. The region outside the event horizon is still mostly vacuum, but the geometry of that vacuum is violently curved. Light that passes near the hole is bent into arcs and rings. Time for an object hovering close to the horizon runs slower compared to a distant observer. If you watched a clock fall toward the horizon, it would appear to tick slower and slower, freezing at the edge and fading away. To the clock itself, time would feel normal until tidal forces became overwhelming. Those tidal forces are another way vacuum enforces separation. Near a small black hole, the difference in gravity between your feet and your head becomes enormous over a short distance. Your body would be stretched in one direction and squeezed in others, a process often called spaghettification. In larger holes, the gradients are gentler at the horizon, but as you fall inward, the curvature grows stronger. No signal you send once inside can make it back out. Whatever you are, whatever you know, becomes causally isolated from the rest of the cosmos. These horizons are not just science fiction hazards for unlucky astronauts. They are fundamental features of the vacuum. Around any mass, there is a region where escape is hard, and around a black hole, there is a sharp boundary where escape is impossible. On the larger scales, there is a cosmological horizon beyond which galaxies drift away faster than signals can catch up. In both cases, the emptiness between things, combined with the finite speed of influence, draws invisible lines that nothing can cross. When you pull all this together, a strange picture emerges. The universe is full of connections. Gravity reaches across light years, photons ferry information from distant suns, entangled particles can remain correlated across vast separations. Yet at the same time, the very laws that allow those connections also impose hard limits. The vacuum will carry your message, but never faster than its strict speed. It will let you watch the past but not see the present beyond a certain distance. It will let you approach certain regions but not leave them again. In this sense, isolation is not an accident. It is baked into the geometry and rules of empty space. Every star, every planet, every galaxy lives inside its own bubble of possible influence, widening slowly but never reaching all that exists. In the next part, we will switch gears and look not just at the physical limits of the vacuum, but at what it feels like on a more human level. Silence, the absence of air, and the strange philosophical question of whether nothingness can ever truly exist at all. In the last part, we saw how the vacuum uses distance, light speed, and gravity to separate worlds and trap information. Now we're going to look at something you can feel more directly: silence. On Earth, true silence barely exists. There is always wind, traffic, insects, the hum of electricity, the quiet rhythm of your own breathing. We live inside a permanent ocean of sound. The vacuum of space strips that away and leaves behind a kind of silence we're not built for. Sound is nothing more than vibration passing from one piece of matter to the next. Air molecules bumping into their neighbours, water molecules jostling one another, solid atoms wiggling in place. Your ear converts those tiny pressure changes into nerve signals, and your brain calls it a voice or a song or a thunderclap. Take away the medium, and there is nothing to wiggle. No chain of collisions, no pressure wave, no sound at all. That is why explosions in movies set in space are dramatic but wrong. In a real vacuum, a star could tear itself apart in a titanic eruption, and you would hear exactly nothing if you floated nearby without a suit. You would see blinding flashes of light and radiation. You would feel the impact if debris hit you, but the event itself would unfold in absolute silence. The universe does not provide a soundtrack. We add that part afterwards. For astronauts, the weirdness is more intimate. Inside a spacesuit there is air, so they hear the hiss of life support pumps, the click of valves, their own breathing, their own voice travelling through their skull. Outside the suit, the vacuum carries no whispers. Two astronauts could be a few meters apart, facing one another, waving their arms, and yet without radios they would be as mute as stones. Empty space shears away a whole sense that evolution spent hundreds of millions of years refining. So, acoustically, the vacuum is as close to nothing as we can get. No medium, no sound. That might tempt you to think that nothing at all is happening there. Yet at the very same time, that silent darkness can be brilliantly bright. Light has no trouble crossing a vacuum because light is not a vibration of matter. It is a ripple in an electromagnetic field that is already present everywhere, even when there is no air or dust. That field is one of the many invisible structures that turn emptiness into something far more interesting. Electric and magnetic fields are not optional extras that appear only near wires and magnets. They are part of the fabric of the vacuum. Place a single electric charge in space, and the field around it rearranges. The strength of the field at each point tells other charges how they would feel a force if they wandered there. You do not need a medium for that. The empty region between the charges is what carries the field. It is how the universe encodes potential influence from one place to another. When you bring quantum ideas back into this story, things become even richer. The vacuum is not just a stage where fields sit. It responds to those fields in subtle ways. Around a charged particle, the quantum vacuum stirs with virtual pairs of oppositely charged particles that appear and vanish. These pairs briefly arrange themselves in a pattern that partly screens the original charge. To a distant observer, the charge seems weaker than it would be in a truly empty void. In effect, the vacuum behaves a little like a material that can be polarized. In ordinary materials, molecules shift slightly in response to an electric field, their positive and negative charges separating just enough to reduce the field inside the material. We call such substances dielectrics. In the quantum world, the vacuum itself plays a similar role. It has an effective ability to be polarized, even though there are no permanent molecules there. So the emptiest space you can imagine still has properties that can be measured, catalogued, and folded into the equations of physics. Light travelling through this structured vacuum is not a bead rolling on a bare wire. It is a disturbance of the electromagnetic field moving through a medium with specific traits. The speed of light in vacuum is one of those traits, setting the absolute limit for how fast information and causal influence can propagate. In more exotic circumstances, such as near incredibly strong fields, the quantum vacuum can even behave differently, changing how light moves. These effects are tiny in everyday life, but they are another reminder that the vacuum is not a lack of reality. It is a particular state of a very real thing. Space-time itself seems to behave in a comparable way. When massive objects collide, they send out gravitational waves, ripples in the geometry of the vacuum. These waves pass through everything, compressing and stretching space in tiny amounts as they go. They can cross billions of light-years of near-perfect vacuum without fading much, because what is oscillating is not matter. It is the structure of space and time themselves. So in the grandest sense, even gravitational silence is an illusion. The vacuum hums with waves too faint and slow for us to feel, but not too faint for careful detectors to notice. All of this raises a deep and slightly unsettling question. Is true nothingness even possible? When you say there is nothing in a region of space, you usually mean no particles, no atoms, no dust, no light. But as long as that region has geometry, As long as it has distance and duration and can host fields and laws, it is not nothing in a philosophical sense. It is something, a structured arena with specific rules. Modern physics treats that arena as fundamental to what existence means. For much of history, thinkers argued about this. Some favour the idea that space is an absolute container that exists even if there is no matter in it. Others thought only relations between objects are real, and that empty space without things in it is a meaningless concept. Einstein complicated the picture by tying space and time together and letting their geometry depend on matter and energy. Quantum field theory complicated it further by filling every region with fields that have ground states and fluctuations, even in the absence of particles. There is another twist. Our universe might not have only one possible vacuum. In high-energy conditions, such as those in the early universe, the fields that fill space can settle into different patterns. As the cosmos cooled, those patterns may have changed through phase transitions. Forces that were once united split into separate behaviours. What we call the vacuum today could be one particular configuration among many possible ones. In that sense, vacuum is not an absolute idea. It is relative to the underlying theory describing the fields. You can imagine a thought experiment where you try to peel away more and more layers. First you remove all particles, then you somehow turn off all fields, then you erase the geometry, no distances, no durations, no directions. When you reach the end of that ladder, there's nothing left to talk about, not even an empty container. That would be true nothingness. But whatever that is, it does not seem to be what our universe offers anywhere. Every patch of our reality comes with at least a space-time structure and some field content. We never encounter the absolute void in practice. At a human level, we still use the word nothing to describe empty rooms, quiet days, gaps in conversation. We feel discomfort in silence and bare spaces and often rush to fill them with sound, decoration, distraction. Some people look at the cosmic vacuum and feel a similar discomfort, a kind of existential vertigo at the idea that most of reality is not occupied by warm, familiar matter. Others see in that emptiness a kind of peace, a reminder that our dramas unfold on a backdrop that is vast, indifferent, and strangely beautiful. Either way, the message from physics is humbling. When you stare into what looks like nothing, you're actually looking at something deeply structured. A silent sea of fields, a flexible geometry that tells matter how to move and is in turn told how to curve, a quantum medium whose subtle jitters helped sculpt galaxies. In the next part, we'll trace how that medium evolved from an early state that was anything but empty, a hot, dense fireball filled with light, into the cold, near vacuum we see today, and how that same emptiness now guides the ultimate fate of the cosmos. Right now, if you walk outside on a clear night and look up, the universe feels cold and mostly empty. Stars are tiny, space is dark, and the vacuum dominates almost everything. It is easy to imagine that it has always been like this and will always be like this. In reality, the cosmos began in a state that was the opposite of empty. It was hot, dense, bright, and crowded, more like the inside of a star than the space between them. In this part, we're going to trace a single line through time, from that early fireball to a far future where almost nothing happens, and see how emptiness slowly takes over. Win the clock back to the first few 100,000 years after the Big Bang. The universe then was a thick, glowing plasma of protons, electrons, and photons. Matter and light were locked together. Free electrons scattered photons constantly, so light could not travel far without bouncing into a charged particle. The cosmos was opaque, like the interior of a star or the surface of the sun. There were no stars yet, no galaxies, just a hot fog filling all of space. As the universe expanded, that fog cooled. Eventually, temperatures dropped enough that protons and electrons could combine and stay together as neutral hydrogen atoms. When that happened, something dramatic followed. With far fewer free electrons around, photons were suddenly able to travel long distances without being scattered every moment. The universe went from opaque to transparent. light that had been trapped in the plasma was released and began streaming across the cosmos. We still see that light today. It has been travelling for more than 13 billion years, stretched by cosmic expansion from searing high-energy radiation into a gentle bath of microwaves. We call it the cosmic microwave background. It fills all of space almost perfectly evenly, with a temperature just under 3 degrees above absolute zero. No matter where you look in the sky, if you tune the right instruments, you find the same faint glow. It is the afterglow of the hot young universe, still whispering through the present-day vacuum. At first glance, this background looks smooth, almost the same temperature in every direction. That near uniformity is part of the mystery and beauty of the cosmos. But if you look very closely, you find tiny variations. Some spots are a little hotter, some a little colder. These differences are incredibly small, just a few parts in 100,000. Yet they carry a map of the early universe written in temperature. Slightly hotter regions correspond to slightly denser patches of matter, and slightly colder regions to slightly thinner ones. Those little ripples are the stretched and frozen fingerprints of the quantum fluctuations we met earlier. In the early plasma, gravity tried to make denser regions collapse, while radiation pressure pushed back. That tug of war created oscillations, like sound waves ringing through the young universe. When atoms formed and the universe became transparent, those waves left their imprint on the escaping light. Today, we see that imprint as a delicate speckle pattern in the cosmic microwave background, a pattern that encodes the seeds of every galaxy that would ever form. From that moment on, emptiness began to win. As the universe expanded, matter thinned out. Gas fell into those slightly denser regions and began to form the first stars and galaxies, but the average density of the cosmos kept dropping. The photons in the background kept streaming, their wavelengths stretched longer and longer by expansion. What was once a blinding white-hot fog became a dim microwave hum barely above the coldest possible temperature. The early universe was crowded and bright. The modern universe is sparse and dark. Fast forward to the present. Stars shine by fusing light elements into heavier ones, turning mass into energy. That process cannot continue forever. Stars burn through their fuel. Massive ones live fast and die young in supernova explosions. Smaller ones like our Sun take their time, lasting billions of years before swelling and shedding their outer layers. The smallest red dwarf stars sip their fuel so slowly that they can burn for trillions of years, far longer than the universe has existed so far. But even they eventually run out. As time stretches onward, star formation slows. Gas reservoirs are used up or heated and spread too thin to collapse. The bright phase of starlight gradually ends. Galaxies that once glowed with young blue stars settle into a quieter existence, populated mostly by long-lived red stars and stellar remnants. The night skies of future worlds will look redder and dimmer as the population of massive short-lived stars dwindles. After enough time, even those long-lived stars will fade. What remains are stellar corpses, white dwarfs, which slowly cool from hot blue embers to cold black lumps. Neutron stars, city-sized spheres of ultra-dense matter, black holes of various sizes, planets, asteroids and comets, either frozen in stable orbits or flung away into intergalactic space. The universe enters a phase where the main sources of light are the slow cooling of remnants and the occasional rare collision. On yet longer timescales, gravity continues to rearrange matter. Some white dwarfs might collide and briefly reignite in thermonuclear explosions. Some neutron stars and black holes merge, releasing bursts of gravitational waves. But such fireworks become rarer as the universe expands and matter spreads out. If certain theories are right, even protons inside atoms may eventually decay over unimaginable spans of time, turning what we think of as solid matter into lighter particles and radiation. The details are still uncertain, but the trend is clear. Ordered structures give way to simpler ones. Energetic differences smooth out. Meanwhile, dark energy keeps doing its quiet work. Space expands faster and faster on the larger scales. Distant galaxies slip beyond each other's horizons, unable to exchange light or matter ever again. Each gravitationally bound group of galaxies becomes an island universe adrift in a deepening void. From the point of view of any future astronomer trapped in such an island, the cosmic microwave background will continue to cool and fade. Its wavelengths stretch so far that it becomes almost impossible to detect. In that far future, the universe approaches what physicists call heat death. Heat death does not mean everything freezes in the everyday sense. It means that usable energy differences disappear. There are no longer temperature contrasts you can exploit to do work, no more free energy to run complex processes on large scales. Everything reachable has fallen toward the same uniform state. Matter is thin, radiation is cold and diluted, and almost nothing interesting happens spontaneously. The vacuum dominates completely. The rare remaining particles and photons drift in an enormous, almost perfectly empty volume. It is a bleak picture at first glance. A universe that begins in a flash of light and ends in a whisper of cold radiation. But look again, and there is another way to see it. The same physics that drives the universe toward that simple, empty state is what made its earlier complexity possible. The expansion that thins matter allowed galaxies and planets to emerge without collapsing into a single black hole. The drive toward higher entropy, toward more ways to arrange things, allowed chemistry, life, and thought to arise as temporary patterns exploiting energy gradients. We live in a special middle era. The cosmos is old enough that heavy elements exist, stars and planets are common, and the background radiation is cool and gentle rather than lethal. It is still young enough that stars shine, galaxies are visible, and the sky carries clear evidence of its own origin. One day, very far from now, that evidence will fade beyond reach. The vacuum will keep expanding, the last traces of structure will dissolve, and the story of matter will quietly end in a sea of almost nothing. From the first opaque plasma to the last cold photon, the main character of that story is not the stars, but the emptiness between them and within them. The cosmic microwave background is our best snapshot of the universe when emptiness was just beginning its long takeover. Heat death is the imagined final chapter where emptiness wins completely. In the next part, we will confront one of the strangest puzzles this picture creates: the enormous mismatch between how much energy theory says the vacuum should have and how much it seems to actually have, and what that might tell us about why our particular universe is even possible. By now we have met dark energy as a quiet background actor, a tiny push built into empty space that speeds up cosmic expansion. That idea is already strange, but there is a deeper problem hiding behind it. When physicists try to calculate how much energy the vacuum should have, the numbers they get are ridiculously huge compared to what the universe actually shows us. Not a little off by a factor that breaks your intuition. It is sometimes called the worst prediction in physics. Beneath that embarrassment sits a haunting question. Why does the vacuum have the gentle value it does, and not a value that would have made a universe like ours impossible? The story starts with the quantum fields we met earlier. Every field has a lowest energy state, its ground state. Even when there are no real particles around, there is still a baseline level of jitter. In quantum theory, each mode of vibration of a field contributes a tiny piece of energy to the vacuum. You can think of these modes like musical notes on an infinite instrument. For each note, there is a minimum energy that cannot be removed. If you add up the contributions from all those modes, you get what is called the 0-point energy of the field. Mathematically, the sum blows up. It diverges to infinity unless you impose a cutoff, a highest frequency beyond which you stop counting. A natural place to stop might be around the Planck scale, where we expect our current theories to break down anyway. Even with that generous excuse, the answer you get for the vacuum energy density is enormous. When cosmologists infer the energy density of dark energy from observations, they find a very small value on everyday scales, enough to drive acceleration over billions of years, but so tiny that in a laboratory it is nearly impossible to notice directly. If you compare that observed value with the naive quantum field theory estimate, the difference is staggering. The predicted value can be roughly 10 to the power of 120 times larger than what we see. Imagine predicting that the weight of a coin should be as heavy as a galaxy, and then discovering that it is just a coin after all. We do not usually tolerate that kind of mismatch in physics. When theory and observation disagree by a factor of 2, people panic and write papers. A factor of 10 is a crisis. A factor of 10 to the power of 120 is a sign that something profound is missing from our understanding. It means that either our method of computing vacuum energy is wrong, or some unknown mechanism cancels almost all of it, leaving behind only the tiny residue we observe as dark energy. One simple-sounding idea is cancellation. Perhaps there are positive contributions to vacuum energy from some fields, and negative contributions from others, and when you add them all up, the result is almost zero. Almost, but not quite. That would require a level of fine balance that feels unnatural. You would have to tune the parameters of your theory to astonishing precision so that gigantic quantities nearly cancel, leaving a tiny remainder. There is no known symmetry that demands this, no deeper reason we have found that forces the vacuum energy to be so small yet not exactly zero. Another possibility is that we are thinking about vacuum energy the wrong way, and that some future theory of quantum gravity will show us that the contribution from high-frequency modes does not count in the way we expect. Maybe space-time at the smaller scales does not allow the naive piling up of zero-point energies. Various ideas along these lines have been explored, but so far none has emerged as a clear, widely accepted solution. The mismatch remains, sitting there like an unsolved riddle at the heart of modern cosmology. There is also a more radical line of thought. Maybe the vacuum energy in our universe is not uniquely determined by deep laws at all. Maybe there are many possible vacuum states, each with its own value of energy density and other parameters, and different regions of a larger multiverse realize different options. In most of those regions, the vacuum energy might be huge and violent. Expansion would be so rapid that matter could never clump into galaxies. In others, it might be large and negative, causing the universe to recollapse so quickly that stars never have time to form. In that landscape of possibilities, life as we know it could only emerge in the rare patches where the vacuum energy is small enough and gentle enough to allow galaxies, stars, and planets to exist for billions of years. We find ourselves in such a patch not because it is typical, but because it is one of the few where observers can arise and ask the question at all. This way of reasoning is often called the anthropic principle. It does not tell you why the multiverse exists, or why its menu of vacua looks the way it does. It simply notes that your existence filters what you can expect to observe. Some physicists dislike this line of thought, because it feels like giving up on a more predictive explanation. Others see it as a natural consequence of combining inflationary cosmology with theories that have many possible vacuum states. Either way, it does something psychologically important. It reframes the smallness of dark energy not as an absurd accident, but as a selection effect. Out of all the ways vacuum could have turned out, we wake up in one of the few that is not instantly lethal to complexity. There is another twist in this story. The value of dark energy does not just make our current universe habitable, it also controls how much of the universe is visible to us at all. Because dark energy drives acceleration, there is a horizon beyond which galaxies are forever receding faster than light can bridge the gap. Over time, more and more galaxies that we can see today will slide beyond that horizon. Their light, emitted now, will never reach us. Our observable patch will shrink in terms of what it contains, even as its physical size grows. Far in the future, any astronomers living in a typical galaxy group will look out and see only their local cluster. the cosmic microwave background will have faded and redshifted until it is effectively undetectable. The evidence that the universe began in a hot, dense state and then expanded will be hidden from them by the very dark energy that shaped that history. They might conclude that their little island is all that exists, a static pocket of stars in an eternal dark. The grand story we tell today about the Big Bang and cosmic evolution is only possible because we live at a time when the sky still carries that information. So the vacuum energy problem is not just a technical glitch in equations. It is tied to why the universe is the way it is, why we are here at this particular cosmic moment, and what future observers will be able to learn. A slightly different value could have erased galaxies from existence, or erased their evidence from the sky. The emptiness we drift in is tuned in a way that seems absurdly delicate, and we do not yet know whether that delicacy hides a deep lore, a vast multiverse, or something stranger than either. In the next part, we will follow a related line of thought even further, turning to the idea that our vacuum might itself be only a temporary state. We will explore the fields that give particles their mass, and the unsettling possibility that the universe we know could, in principle, tunnel into a different vacuum entirely, rewriting the rules of reality in an expanding bubble that nothing could outrun. In earlier parts, we treated particles as ripples in invisible fields that fill all of space. That idea is strange, but it pays off in powerful ways. It explains not only why we see different kinds of particles, but also why they have mass at all. In this part, we're going to walk into one of the strangest corners of that picture, the possibility that the vacuum itself might not be the absolute ground state of reality, but a temporary arrangement that could, in principle, change. If that happens, the universe would not politely adapt, it would be rewritten. Let us start with the fields. Every kind of particle you know from physics books is an excitation of some underlying field. Electrons are ripples of the electron field. Quarks are ripples of quark fields. Photons are ripples of the electromagnetic field. In the absence of ripples, those fields are still there, stretched through the vacuum in their lowest energy configuration. The vacuum is not the absence of fields. It is what all the fields are doing when nothing obvious seems to be happening. Mass adds a twist to this story. Photons, the particles of light, are massless. They move at the cosmic speed limit and never slow down. Many other particles, like electrons and quarks, carry mass. They can be at rest, they resist acceleration, and they feel gravity more strongly. Why should some ripples be massless and others heavy? For a long time, this was a deep mystery. Then a new character joined the cast, the Higgs field. The Higgs field is another field that fills all of space, including the vacuum between galaxies and the emptiness inside your body. Its special feature is that even in its lowest energy state, it does not sit at zero. It has a non-zero value everywhere, like a background fog. Particles that interact with this field pick up inertia. You can imagine them moving through a crowded room and feeling a kind of drag that makes it harder to change their motion. The stronger their interaction with the Higgs field, the more mass they have. In this picture, mass is not something particles carry as a permanent label from birth. It is a measure of how strongly they are tied to the ever-present Higgs field that permeates the vacuum. When physicists smashed particles together at high energies in colliders and discovered the Higgs boson, they were not just adding one more particle to a list. They were confirming that this field, and its strange non-zero value in empty space, is really there. The vacuum we live in is not a simple nothing. It is a medium with a particular pattern frozen into it. Here comes the unsettling part. In many physical systems, the lowest energy state is not obvious. A bull sitting in a shallow valley may seem stable, but if there is a deeper valley hidden behind a hill, that bull is only metastable. It can sit in the shallow valley for a long time, but a big enough push can send it over the hill and down into the deeper true minimum. The same idea can apply to fields. The configuration we call the vacuum might be a local minimum of energy, rather than the absolute minimum. When physicists analyse the Higgs field and how it interacts with other fields, such as the top quark field, they can ask a simple but profound question. Is our current vacuum configuration guaranteed to be the lowest possible energy, or could there be another arrangement far away in field space that has even lower energy? The answer, based on measurements so far, is both reassuring and unnerving. It seems plausible that our vacuum is metastable, not obviously doomed, but not guaranteed to be forever safe either. If the vacuum is metastable, then in principle a transition to the lower energy state could occur through a quantum process called tunneling. Imagine that ball in the shallow valley again. Classically, it would need enough push to climb over the hill. Quantum mechanics allows a different path. With an incredibly small probability, the ball can simply appear on the other side of the hill, as if it had tunneled through. For the Higgs field, that would mean that in some tiny region of space, the field configuration could randomly change to the true vacuum state. If that ever happened, the consequences would be dramatic. A bubble of the new vacuum would form at the tunneling site. Inside that bubble, the value of the Higgs field and possibly other fields would be different. That means the masses of particles, the strengths of forces, and the basic rules of atomic and nuclear physics could all change. The bubble would be energetically favoured, so it would expand, driven outward at nearly the speed of light, eating the old vacuum as it goes. There would be no warning. Because the bubble wall moves essentially as fast as causality allows, no signal could outrun it. One moment the universe in some region would be as it always has been. The next moment the advancing front of the new vacuum would sweep through, rewriting the laws of physics on its way. Atoms would not survive the transition. The structures built from them, stars, planets, living beings, would not have a chance to adapt. It would not be an explosion in the usual sense. It would be a global change of the underlying game. This sounds like a science fiction disaster scenario, and sometimes it is described that way in popular media. In practice, the timescales involved are so colossal that it should not keep you awake at night. The probability per unit time for such a vacuum decay event, given current estimates of the Higgs mass and its interactions, is fantastically tiny. The expected lifetime of our metastable vacuum can be much longer than the current age of the universe, perhaps by many orders of magnitude. On those scales, other fates for the cosmos, like heat death or black hole evaporation, may play out first. Still, the possibility is conceptually important. It reminds us that the vacuum is not a rigid backdrop ordained from eternity. It is a configuration that could have been different and might one day be different still. It ties back to the earlier fine-tuning puzzle. Our current vacuum energy is small and positive, a value that allows galaxies and complexity. That value is tied to how fields like the Higgs are arranged. If the universe ever tunnels to a deeper vacuum, that energy could change sign and magnitude in ways that rule out familiar structure altogether. Einstein enters the story again here. When he introduced the cosmological constant to make a static universe possible, he was effectively adding a fixed energy density to empty space. Later, when expansion was discovered, he reportedly called that his biggest blunder. Dark energy resurrected the cosmological constant as a real feature of the vacuum. Now the Higgs field and the idea of vacuum metastability add another layer. The constant energy of empty space might not be fixed forever. It could in principle jump, taking the geometry of space-time and the behaviour of matter with it. From our vantage point, the vacuum feels permanent. The laws of physics seem stable. Apples fall, light moves at the same speed, atoms behave. Yet deep in the equations there is this quiet possibility of change, a reminder that even what we call nothing is part of a dynamic landscape. The fact that we live in a vacuum gentle enough and stable enough for stars and life to exist for billions of years is another piece of the cosmic puzzle. Is it an accident in a vast multiverse, a consequence of deeper principles we have not yet uncovered, or a temporary plateau on the way to a very different universe? In the next part, we will step back from this unsettling possibility and look at how we actually study the vacuum in laboratories and in space. We will see how tiny shifts in atomic energy levels, subtle forces between metal plates, and minute anomalies in spacecraft trajectories all became clues in our attempt to measure nothing. Along the way, we will reconnect this grand cosmic story to the everyday matter around you and inside you, which is, in the end, nothing more than patterns of fields and vacuum arranged into the shape of a living world. We have spent a lot of time talking about emptiness in a grand, almost philosophical way. Quantum foam, dark energy, cosmic horizons. Now it's time to get our hands dirty and ask a very practical question. How do you measure something that is not there? In physics, the answer is almost always the same. You watch what it does. You look at how nothing tugs on metal plates, shifts the colours of atoms, bends the paths of light, and even nudges lonely spacecraft on their way out of the solar system. Think back to the Casimir effect we met earlier. Two very flat metal plates facing each other in a vacuum chamber, separated by a tiny gap. Pump out the air, cool things down, eliminate every obvious source of pressure, and you might expect perfect stillness. Instead, when you measure carefully, you find that the plates attract each other with a small force. The arrangement of vacuum fluctuations is slightly different between the plates and outside them, and that imbalance shows up as a push. This is not an easy experiment. The force is minuscule, and the plates must be aligned with ridiculous precision. Stray charges, rough surfaces, and tiny vibrations can all ruin the measurement. Yet many groups have done it with different techniques, and the results line up with the predictions of quantum field theory. The Casimir effect has become one of our cleanest ways of saying the vacuum is not blank. It has structure that can reach out and move things. Atomic physics offers another beautiful window into nothing. Take the hydrogen atom. One proton and one electron, the simplest atom you can write down. If you solve the equations for an electron in the electric field of a proton, you get specific energy levels. Those levels correspond to specific colours of light when the electron jumps between them. When experimenters measured those colours with high precision, they found tiny shifts compared to the simple theory. One of those shifts is called the Lamb shift, named after the physicist who first measured it. The explanation lives in the quantum vacuum. The electron is not moving in a perfectly clean electric field. The vacuum around the proton is busy with fleeting particle pairs and fluctuating fields. That activity slightly alters the effective field the electron feels, and therefore slightly alters its energy levels. When you shine light on hydrogen and look at the exact frequencies it absorbs and emits, you are listening to the whisper of vacuum fluctuations changing the music by a small but measurable amount. Small corrections like this appear all over precision physics. The magnetic moment of the electron, a measure of how strongly it behaves like a tiny magnet, is shifted by its interaction with the vacuum. The way light travels through strong fields can be altered. These effects are subtle, but they add up to a body of evidence. When our best theories include vacuum fluctuations, they match experiments to many decimal places. When we pretend the vacuum is truly empty, they do not. On much larger scales, we study nothing by watching how it bends light. Gravity is not a force acting at a distance in modern physics. It is the curvature of space-time itself. When a massive object sits in the vacuum, it warps the geometry around it. Light passing through that region follows the bent paths, just as a car follows a curved road. This bending is called gravitational lensing. Look at a massive cluster of galaxies. Behind it, more distant galaxies send their light across billions of light years of near-empty space. As that light passes near the cluster, it is deflected. To an observer on Earth, the background galaxies appear distorted into arcs and streaks. In some cases, their images are multiplied. With sensitive surveys, you can even measure tiny distortions in the shapes of many galaxies and use them to map the invisible mass in the foreground. That invisible mass is mostly dark matter spread through the vacuum in a wide halo. By analysing the lensing patterns, astronomers can reconstruct how that unseen matter is distributed, even though it never shines or absorbs light. In this way, space-time and vacuum become tools for weighing things. You never touch the dark matter directly. You watch how it makes light curve as it travels through the emptiness. Sometimes our attempts to measure nothing lead us down strange paths. Consider the story of the Pioneer spacecraft. Pioneer 10 and Pioneer 11 were robotic probes launched in the 1970s to explore the outer solar system. After their main missions, they continued on into deep space along long, graceful arcs. As they flew, engineers tracked their positions by bouncing radio signals off them and measuring the tiny shifts in frequency caused by their motion. For years, the data showed something odd. The spacecraft seemed to be slowing down ever so slightly more than expected, as if there were a tiny extra pull acting on them, directed toward the sun. The effect was unbelievably small, comparable to the weight of a sheet of paper on your hand. Yet it was persistent and real in the data. Some people wondered whether it pointed to new physics, a modification of gravity at large distances, or some unknown feature of the vacuum in the outer solar system. The mystery eventually found a more mundane answer. Detailed studies showed that the spacecraft were radiating heat from their power systems in a slightly uneven way. Photons carry momentum. When more thermal radiation was emitted in one direction than another, the spacecraft experienced a gentle recoil. Over years, that tiny push added up to the observed deviation in their paths. The Pioneer anomaly became an example of how important it is to be humble with anomalies. The vacuum did not reveal new laws that time. It reminded us that our machines themselves can be the loudest whisper in the data, that humility matters because the vacuum is both subtle and easy to blame. Any unexplained effect in space can be tempting to attribute to dark matter, dark energy, or some new property of emptiness. Sometimes those guesses are right, many times they are not. The path to understanding nothing runs through careful accounting of everything, including your own instruments. To bring this back to your everyday world, look around the room you're in. The table, the walls, your own body, all feel solid and continuous. Yet at the atomic level, they are mostly empty space, organized by fields and quantum rules. The rigidity of a crystal lattice, the springiness of a piece of metal, the transparency of glass, and the flexibility of a polymer all emerge from how electrons fill energy levels and how atoms sit in patterns surrounded by vacuum. In a crystal, atoms line up in repeating structures. Electrons move in bands of allowed energies and are blocked from others. When an electron leaves a position in one of these bands, the absence behaves like a particle in its own right. Physicists call it a hole, a kind of positive charge that moves through the lattice. It is a reminder that even the missing parts of a pattern can act like something real. Your computer chips and phone screens depend on these effects. They are devices built from controlled emptiness and carefully arranged gaps in energy. Inside a molecule of water, the hydrogen and oxygen atoms share electrons in bonds that are really shared patterns in their overlapping quantum clouds. Those clouds are mostly space. The shapes of the bonds, the angles between them, and the way water molecules attract one another give water its strange properties. Surface tension, the way it flows, the way ice floats, all of that emerges from how mostly empty electron clouds arrange themselves. The same is true at a much higher level of complexity for the long molecules of DNA and proteins that make up your cells. So when you touch the world, you are feeling mostly the effects of fields and rules in vacuum, forces that rise sharply when electron clouds begin to overlap, vibrations in lattices that carry sound, tiny shifts in energy that determine whether a material conducts electricity or blocks it. Everyday substance is not the opposite of emptiness. It is emptiness organized in specific ways. Across all these scales, from Casimir plates to galaxy clusters to the chemistry of life, we keep using the same strategy. We cannot hold nothing in our hands, so we watch how it modifies something else. A shift in a spectral line, a bend in a ray of light, a tiny drift in a spacecraft path, a property of a solid. Each one is a clue that what we casually call empty space is doing quiet, complicated work. In the next part, we will push this idea further and look at how the vacuum does not only separate things, it also connects them. We will explore quantum entanglement and the early universe in which fields and vacuum were in a much more turbulent state. Along the way, we will see how emptiness can be a medium not just of isolation, but of deep underlying unity across the cosmos. So far, emptiness has mostly felt like a force for separation, distance, horizons, one-way traps around black holes. Now we're going to flip the angle and look at something that seems to laugh at distance: quantum entanglement. It is one of the clearest hints that the vacuum is not just a gap between things, but a kind of hidden fabric that can link events across space in ways that feel almost conspiratorial. To understand the early universe and the deep structure of reality, we have to make peace with this very strange kind of connection. Start with a simple picture. Imagine two particles created together in a way that ties some of their properties into a shared pattern. For example, their spins could be linked so that if one is measured to be up along some direction, the other will always be found down along that direction, no matter how far apart they are when you finally check them. Before you measure, quantum mechanics says the pair is in a superposition of possibilities, not fixed outcomes. The two particles are not separate things with hidden settings. They share a single, joint state. This is what we call entanglement. It means the full description of the system cannot be broken into independent descriptions of each part. When you measure one particle, you do not send a signal through space to tell the other what to do. Instead, you reveal a correlation that was built into the joint state from the beginning. Experiments have tested this over and over, closing loopholes, and the universe consistently refuses to behave like a simple theory with secret local settings. The correlations are stronger than any local hidden rules can explain. Notice what this does to our picture of empty space. You can put those two entangled particles light years apart, drifting through vacuum with almost nothing between them. The emptiness does not weaken or break the correlation. When you finally measure, you still see the pattern. The vacuum is not a noisy medium that scrambles quantum links over distance the way fog scrambles light. At a fundamental level, the state of the field describing both particles spans the gap. The separation is real for signals and forces, but not in the same way for quantum correlations. Now zoom out from two particles to a whole field. In quantum field theory, even the vacuum state of a field is entangled. Different regions of space share subtle correlations, even when there are no real particles present. Cut the universe into two halves in a thought experiment, and the vacuum on one side is not independent of the vacuum on the other. They are part of a single global state. This is one reason some physicists think that space-time geometry itself might emerge from patterns of entanglement. The idea is still speculative, but it captures something deep. The structure of emptiness and the structure of connection may be two sides of the same coin. This becomes especially important when we think about the early universe. Right after the Big Bang, before atoms and galaxies, the fields that fill space were in a very different state. Temperatures were so high that distinctions between different forces blurred. Electromagnetic and weak nuclear forces acted as one. At even higher energies, other forces may have unified as well. Instead of each field settling into the pattern we see today, the vacuum was in a more symmetric, tightly coupled configuration. As the universe expanded and cooled, that symmetry broke. Fields underwent phase transitions, a bit like water freezing into ice, but in a space of abstract values rather than ordinary positions. The Higgs field settled into a non-zero value. Forces separated into distinct behaviours. Different possible vacuum states became available, and the universe fell into one of them. In each transition, entanglement patterns shifted. The vacuum reorganised itself, and the rules for how particles gain mass and how they interact changed with it. One of the most dramatic episodes in this story is the suspected period of inflation. In many models, the very early universe was dominated by a form of vacuum energy, much larger than the dark energy we see today. That high-energy vacuum acted like a powerful temporary engine, causing space to expand at an almost unimaginable rate. Distances doubled again and again in a tiny fraction of a second. During this era, quantum fluctuations of the fields, including the inflating field itself, were stretched from microscopic scales to astronomical ones. Those stretched fluctuations were not random noise in the usual sense. They were quantum in origin, with definite patterns and correlations set by the initial state of the fields. As inflation ended, the vacuum energy driving it decayed into a hot soup of particles and radiation, in a process often called reheating. The universe became a dense, glowing plasma again, but now with baked-in variations in density and temperature inherited from those amplified vacuum fluctuations. Gravity later magnified those variations into galaxies and clusters. Entanglement in the early vacuum left fingerprints on the sky and in the large-scale structure we map today. Black holes bring entanglement and vacuum dynamics together in another surprising way. We normally think of black holes as regions where things fall in and never return, yet quantum mechanics and the structure of the vacuum suggest they are not completely black. Near the event horizon, the vacuum is a restless sea of fluctuations. In a simplified picture, pairs of particles flicker into existence. One member of a pair can fall into the black hole, while the other escapes to infinity. To a distant observer, this looks like a steady trickle of radiation coming from the black hole itself. This process is known as Hawking radiation. It means that black holes are not eternal. As they emit radiation, they lose mass and very slowly shrink. For a black hole the mass of a star, the evaporation time is vastly longer than the current age of the universe. For smaller hypothetical black holes, the evaporation could be much faster. The details are still an active area of research, and the simple picture of particle pairs is only an illustration, but the underlying message is clear. Quantum properties of the vacuum near horizons have real, macroscopic consequences. They can empty even the darkest regions of their contents over long times. Entanglement is also at the heart of quantum technologies that humans are beginning to build. Quantum computers operate with units of information that can exist in superpositions of 0 and 1 and can be entangled with one another. When you manipulate such a system in the right way, you can perform certain calculations that would take an impractical amount of time on ordinary classical machines. The power does not come from breaking the speed of light or sending messages instantaneously. It comes from exploring the vast space of possible states that the underlying quantum fields allow, and from carefully orchestrating interference among those possibilities. When engineers talk about isolating a quantum device from its environment, they're really trying to control how it is entangled with the rest of the world. Too much uncontrolled contact with the surroundings and the delicate quantum correlations wash out, a process we call decoherence. That environment is mostly vacuum, but not a perfect one. It carries stray photons, vibrating fields, and thermal noise. To make a quantum computer work, you have to shape the way your little artificial system sits inside that restless emptiness. All of this points toward a very different way of thinking about nothing. The vacuum is not just the stuff left over when you remove particles, it is a global state of fields with built-in patterns of entanglement that knit the universe together. Those patterns set the stage for how structure forms, how black holes evaporate, how time and space might emerge at the deepest level, and even how future technologies will handle information. At human scales, entanglement is not something you feel directly. You do not sense the vacuum state that links distant regions, or the early universe correlations imprinted on the cosmic web. You feel gravity, light, warmth, pressure. Yet all of those sensations ultimately ride on the same underlying structure, a set of fields in a particular vacuum, with specific patterns of connection that could, in principle, have been otherwise. In the next part, we will look at one more layer beneath all this. We will treat space-time itself as a medium with its own properties, and ask how the arrow of time emerges from the universe starting in a surprisingly ordered state, and then expanding into more and more emptiness. The flow you feel from past to future turns out to be deeply connected to the growth of the vacuum itself. Up to now, we have treated space as a kind of container, a stage where fields live, particles move, and vacuum energy pushes everything apart. In this part, we're going to do something slightly dangerous for your intuition. We're going to treat space-time itself as a medium, with its own texture and behaviour, and then ask why time inside that medium feels like a one-way street. The strange conclusion is that the arrow you feel from past to future is tied to the way the universe filled itself with more and more emptiness. Start with gravity. In everyday language, we say that masses attract each other. In the language of relativity, that is not quite what is happening. Matter and energy tell space-time how to curve. Curved space-time tells matter and light how to move. If you drop an apple, you're not pulling it down with an invisible force. The apple is following the straightest possible path in a curved geometry. Its path looks like an arc to you because the medium it moves through is bent by Earth's mass. This is not just a metaphor. Light from a distant star passing near the sun really does bend. Time near a massive object really does run more slowly compared to time far away. Space is not a rigid, empty nothing. It is more like an elastic fabric whose shape responds to what is in it. Ripples in that fabric are the gravitational waves we now detect from colliding black holes and neutron stars. The vacuum is not just the absence of matter, it is the geometry itself. At very small scales, this smooth fabric picture may break down. When you shrink your mental ruler toward the Planck length, quantum uncertainty should begin to shake space-time as well as fields. Some ideas picture space-time as made of tiny, discrete pieces, like atoms of volume, woven into a kind of cosmic lattice. Others imagine space-time emerging from deeper patterns of quantum entanglement, so that distance and geometry are not fundamental but derived. We do not yet know which view, if any, is right. What they share is the idea that space-time is something, not nothing. Now look at time. The equations that govern fields and gravity are mostly symmetric between past and future. If you ran them backwards, they would still work. Yet your experience of time is not symmetric at all. You remember yesterday, but not tomorrow. Eggs crack, but do not reassemble. Heat flows from hot coffee into cool air, not the other way. Somewhere between the reversible laws and your irreversible life, an arrow appears. The usual answer invokes entropy. Entropy is a measure of how many microscopic ways there are to arrange a system, while it still looks the same at a large scale. A neat stack of papers on a desk has few possible microscopic arrangements. A messy pile has far more. Left alone, systems tend to move towards states that can be realized in more ways. That is what we call an increase in entropy. A drop of ink spreads in water because there are more ways for the molecules to be mixed than separated. You could in principle reverse every motion and watch the ink gather back into a drop, but that arrangement is so special that it almost never happens by chance. The same logic applies to the universe. What gives time its arrow is not that the fundamental laws prefer a direction. It is that the cosmos started in a state of astonishingly low entropy and has been relaxing toward higher entropy ever since. Early on, matter and radiation were hot and dense, but surprisingly smooth on large scales. That smoothness is the key. For a universe with gravity, a smooth distribution of matter is low entropy compared to a clumped one. There are far more ways to arrange matter into stars, galaxies, and black holes than into a nearly uniform fog. As the universe expanded, two things happened at once. Space grew, creating more room for matter and radiation to spread into. Gravity amplified tiny irregularities, pulling matter into clumps and creating structure. Both processes increased entropy. Radiation cooled and thinned. Massive objects formed and later collapsed. Black holes, with their enormous entropy, emerged as some of the most disordered objects possible. The arrow of time you feel in your day-to-day life is tied to this long cosmic trend of structure forming and then gradually dissolving as the universe expands. Here is where emptiness enters the story in a surprising way. As space expands, the volume of vacuum grows. That gives entropy more room to increase. Imagine a gas trapped in a small box that suddenly finds itself in a larger box. It will spread out, exploring more configurations. In a sense, the expanding vacuum plays the role of the box walls moving outward, granting the universe more possible arrangements to explore. The flow of time from past to future is aligned with the growth of that available space. The low entropy state at the beginning is still a mystery. Why was the early universe so smooth? Why did it start with such a special configuration rather than in a messy high entropy state? Some versions of cosmic inflation try to address this by suggesting that our observable universe is a small patch of a larger, more complicated reality, and that inflation naturally smooths and stretches regions. Yet even then, the question of why the whole system started in a way that allowed inflation to occur remains open. The arrow of time seems to be pointing us toward a deeper question about the initial condition of space-time itself. There is a strange loop here. On one hand, space-time curvature determines how matter moves and clumps. On the other hand, the pattern of matter and radiation determines the entropy and thus the arrow of time. That arrow in turn determines how we experience space-time. We divide events into earlier and later, cause and effect, based on the flow from low to high entropy. You could say that geometry, matter, and the direction of time are all locked together in a single evolving structure. Einstein once thought of the universe as a static four-dimensional block in which past, present, and future all coexist, and our sense of flow is an illusion. There is some truth in that view at the level of the equations, yet the entropy gradient is not an illusion. It really exists, and it picks out one direction in the block as special. The past side of the block is smoother, less clumped, and in a sense less empty. The future side is more structured, more dispersed, and more dominated by vacuum. As dark energy takes over, the expansion of space-time accelerates, and the vacuum becomes ever more important. Local islands of matter remain bound together, but the distances between those islands grow faster than light can bridge. Entropy continues to rise as stars burn out, black holes form and slowly evaporate, and radiation spreads into an ever larger volume. The arrow of time continues to point toward more emptiness, more uniformity, more of the vacuum state dominating everything else. From your point of view, sitting on a small planet around an ordinary star, the flow of time is tied to very local processes, memories stored in your brain, heat flowing from your body to the air, the aging of cells. Yet all of those processes depend on energy gradients created by a universe that began in a special low entropy condition and then expanded. The reason coffee cools in a room and never spontaneously heats up is ultimately related to the fact that the cosmos is relaxing from an ordered beginning into an increasingly empty high entropy state. So when you feel time tugging you forward, you're feeling a global story written into space-time itself. You live in a medium that started out dense and smooth and is now stretching and thinning. The laws that govern that medium do not care about past or future, but the initial state and the unavoidable rise of entropy do. The growth of the vacuum, the fading of structure, and your own sense of before and after are three faces of the same cosmic trend. In the final part, we will bring this all back home. We will ask what it means for beings like us to live in a universe where the main ingredient is emptiness, where time flows toward more vacuum and less structure, and where meaning and value have to be carved out of patterns that are by their nature temporary. By now we have taken emptiness apart from almost every angle. We have shrunk down into atoms, stretched out to the cosmic web, listened to the quiet push of dark energy and the restless jitter of quantum fields. The picture that emerges is unsettling and beautiful. The universe is mostly nothing. Yet here you are, a conscious pattern made of nearly empty atoms thinking about it. In this final part, we're going to bring all of that back to one question. What does it mean to be alive in a universe where the main ingredient is vacuum? Start with a simple but heavy thought. On cosmic scales, you are alone. Not in the melodramatic sense of being unloved or unnoticed, but in the physical sense that the distances between stars and galaxies are so extreme, and the rules of the vacuum so strict that contact with anyone out there is hard. Light speed, expansion, horizons, and the limited lifespan of civilizations create a kind of cosmic quarantine. This is one way to look at the famous question of where everyone else is. People often picture the galaxy as a bustling city that somehow remains eerily quiet. A better image might be a vast dark forest where each tree is a star system, and the spaces between are oceans of vacuum. Civilizations could rise and fall like sparks in that forest. Some may burn brightly for a short time and vanish. Others may last for millions of years, but the timing and spacing may rarely line up so that two are close enough for long enough and look in the right direction at the right moment to notice each other. In that sense, the vacuum does not just separate us in space, it also separates us in time. The Milky Way is more than 10 billion years old. Human technological civilization is only a few thousand years old, and our radio presence is barely a century old. That is a fraction so small it barely registers. Imagine another civilization that peaked 1 billion years ago and faded. Their signals would have washed past long before there were human eyes to see them. Future civilizations might rise long after our radio noises faded into the static. Ships passing in the night, yes, but also in different nights entirely. Yet the same emptiness that keeps us apart also makes long survival possible. If a civilization learns to live gently and manage its resources, it could adapt to the vacuum rather than fight it. You can imagine beings, biological or artificial, that treat interstellar and intergalactic space not as an obstacle, but as a habitat. They might travel slowly, hitching rides on comets and rogue planets, or they might build enormous structures to harvest the thin starlight and the gentle energy gradients that remain in a fading universe. Over vast timescales, life may decouple from planets altogether. It could migrate into space habitats, swarms of machines, or forms we struggle to picture, optimized for low energy conditions. In a universe that is getting colder and emptier, the winning strategy is not speed and consumption, it is patience. Use very little energy, think slowly, stretch each subjective moment over enormous spans of external time. From that perspective, the vacuum is not an enemy. It is the ocean in which long-term existence must swim. Bring the focus back to us for a moment. Humanity has only just stepped off its homeworld. We have sent a few machines to nearby planets and a handful of robots into interstellar space. We have filled Earth orbit with fragile shells of metal that only barely keep the vacuum at bay. Yet those first clumsy steps matter. The first rockets, the first stations, the first spacesuits are like early lungfish wobbling onto land, getting hammered by gravity and sunlight and predator teeth, but proving the transition is possible. One of the most haunting images we have ever taken is the tiny picture of Earth captured by a spacecraft far from home, a faint pale point suspended in darkness. A human voice once described that speck as a home for everyone you have ever known, everyone you have ever heard of, every story and struggle and kindness. You do not need to repeat those words to feel their weight. Against the black sea of the vacuum, our world really is a very small boat. From a physical point of view, that boat is fragile. Its atmosphere is a thin film of gas clinging to rock. Its biosphere is an even thinner skin of chemical complexity balancing on top. Space on all sides is indifferent. Asteroids fly through, radiation streams past, stars slowly change. There is no cosmic law that says the conditions here must remain comfortable for thinking creatures. The vacuum does not promise safety. It offers opportunity and risk in equal measure. From a different point of view, that same smallness is a kind of power, because everything is so far apart and communication is so hard. What you do here matters enormously to the story of life in this corner of the universe. There may be other pockets of awareness elsewhere, but they cannot reach in and fix what we break or write the stories we do not bother to tell. For any beings born here, Earth is not just a random planet. It is the only cradle they get. All the physics we have explored can feel like it points toward meaninglessness. The universe is vast, cold, and impersonal. It will not notice if a species on a small rock survives or vanishes. It will keep expanding whether or not anyone appreciates its beauty. Yet there is another way to see it. Meaning is not something the universe hands down. It is something patterns of matter and energy create internally. A book does not care about its own story. The story lives only in the minds that read it. In the same way, the vacuum does not care about life, but life can care about itself. You are, in a very literal sense, a local organisation of vacuum and fields that has become aware of itself. The atoms in your body were forged in stars and supernova, then cooled in gas clouds, then assembled by chemistry into cells and tissues. The emptiness inside those atoms has not changed. What changed is the pattern. The exact arrangement of particles and fields now embodies memories, preferences, fears, joys. When you look up at the night sky and feel something, that feeling is the universe reflecting on its own structure through you. That sounds grand, but it is also very ordinary. Every moment of kindness, curiosity, or understanding is a local defiance of the general trend toward uniform emptiness. It does not stop entropy rising overall. It does not halt cosmic expansion, but it carves out pockets of order and experience along the way. A civilization that tells stories, does science, builds art, and cares about what happens is a way for the vacuum to host not only matter, but meaning. Seen from that angle, the fact that the universe is mostly empty is not an insult to your significance. It is the condition that makes your existence possible. If everything were dense and chaotic, there would be no quiet, stable regions where chemistry could slow down enough to learn, no protected niches where memory could persist. Emptiness is the canvas that allows stars, planets, and minds to be painted at all. The future will not be kind or cruel on purpose. The vacuum will keep expanding. Structures will form and fade. Horizons will grow. Black holes will evaporate, and the last sources of light will wink out. Somewhere in that story, life in our region may continue, change form, or disappear. You cannot bargain with the laws that govern that path. What you can do is decide how to use the limited time and energy available to you in this brief, hospitable era. In the end, this long journey through nothing leads back to a simple idea. You live in a universe where almost every cubic meter is empty, where the deepest rules care nothing for comfort, and where the final state is likely cold and quiet. Yet inside that universe there are brief flashes of awareness and connection. You are one of them. For a short while you get to notice the void, to understand a little of what it is, and to decide what kind of pattern you want your small corner of it to take. The emptiness does not answer when you talk to it. It does not applaud when you get things right. Still, every act of understanding, every honest question, every attempt to care for this fragile world and the beings on it is a way of saying that even in a universe built from almost nothing, something can still matter.